Okay, is this working? Okay, so first of all, thank you very much to David, Thomas, and Leah for inviting me. Thanks all of you for listening. So this is my title is Trialities of W-algebras beyond the Gaiotto and Rapcak conjectures. So this is in joint work with Thomas and my student Vladimir Kovalchuk. I'm going to start by telling you a little bit about these conjectures and my recent proof with Thomas, and then I'll talk about generalizations. So first of all, today, I'll very briefly talk about W-algebras. So G will be a finite dimensional simple Lie superalgebra, and WKGF will be the corresponding W superalgebra associated to G and some nilpotent even part of G. And W lower KGF will be the simple quotients. And usually for today, it's convenient to replace the level K with the shifted level. So psi will always be K plus H check. And W psi, this psi is not the actual level, it's the shift. And also W lower psi will be the simple. And if that is the principal nilpotent, then I'll just write W psi G. Those are the ones that are best studied. And there are a couple of dualities that they satisfy the element mentioned. So the first one is Feigin and Frenkel duality. It was proven a long time ago in the early 90s. So G is a simple Lie algebra. Then the principal W algebra G is isomorphic as an algebra to the principal W algebra, the Langland's dual Lie algebra. And there's this change of level. The psi prime, the level of the Langland's dual one is up to this laicity of 1 over psi. So this holds for simple Lie algebras. It also holds for principal W algebra with OSP1, 2. So this is a recent theorem of Thomas and Aoki. There's a similar Feigin and Frenkel duality for these W superalgebras. There's another duality. Well, first of all, let me just remind you what the coset construction of vertex algebra is. This is a way of getting new vertex algebras from the old ones. So B is the vertex algebra, and A is any sub-vertex algebra. Then the coset, this is just the analog of the commutant in the theory of associative algebras. It's the subset of elements in B which strictly commute with everything in A. So this is a vertex subalgebra. And strictly commute means they commute as fields, as series in 2 variables. It also means they're trivial OPE. And if B and A are conformal elements, LB and LA, then this coset also has a conformal structure, which is just a difference. So this tells you that the map from A tensor is commutant into B. This is a conformal embedding because it's the same. Let's do a slope vector. Okay, so there's a way of constructing certain W algebras as cosets. So let me first talk about the case where G is simply laced. So this is the result that goes back a few years of Thomas and Timothy. So G is simple and simply laced. And there is I can consider affine vertex algebra of G at level K, and then tensor the simple affine vertex algebra at level 1. There's a diagonal embedding the affine vertex algebra at level K plus 1, where one of the generators was just indexed by element of the Lie algebra. We use the same letter for all of these just maps to the one and so I can consider the coset of the image of this map inside this tensor product. And this is isomorphic to the principal W algebra of G with this change of levels. Okay, so this works for simply based Lie algebras. There's also a coset realization of non-simply based principal W algebra type B, and then of course type C because of Feigin and Frenkel duality. So this has a slightly different form. This was proven by Thomas and Aoki a couple of years ago, and also a different proof is one of our favorites as a consequence of the general, which I'm going to talk about. So for if I take the affine vertex superalgebra OSP1, 2A, it has a copy of the affine superalgebra of SP2A. And I can take this coset. This is isomorphic to this principal W algebra type B as a one-parameter vertex algebra. Maybe I should mention that both of these descend to simple quotients at nice levels. So if K is a positive integer level and more generally a divisible level, then there's an embedding of the simple affine Vertex algebra in the product of the two simple ones, and the coset is the simple W algebra. And similar statement holds over here. There's also a coset realization of the principal W algebra of OSP1 to that I'm not going to mention. Okay, so let me just say briefly what are trialities of W-algebras. So let's say that F is a nilpotent element in G. We complete it to a copy of SL2. I can consider the centralizer of this SL2 in G. So this is some V algebra, super algebra. Trouble with this again. There we go. So first of all, this W algebra G with this nilpotent has an affine subalgebra corresponding to A at some shifted level. And I can consider the coset of this affine algebra. So I'll call this an affine coset. And sometimes I have to do a little bit more. Sometimes it's not enough to just take the coset of this affine algebra, but I have to also take the invariants and there's some root of outer algebras. So in the case where A is type B or D or OSP1 to that, there's an explicit 2 that I should take the coset of. There's also some other cases where I have a larger group of outer algebras. But I usually won't mention that in the equations. I'll affine coset with whatever, maybe with some outer algebras invariants. And so trialities are isomorphisms between three different affine cosets, different W algebras. Typically, one of them is a usual W algebra, the other ones are super algebras. G and G prime and G double prime can be different, and the affine subalgebras can be different. It's not at all obvious that there should exist such trialities, and these are generalizations of both Feigin Frenkel duality and this coset realization. So some of the special cases are these statements that we already had. But these are kind of unifying results, and the proof is uniform. So I'm going to say more today about type A because it's easier to state and maybe for you to understand. But I'll briefly mention something about some Vertex types, and then that'll be maybe half of the talk. And then I'll try to say a little bit about various ways of discussing generalize. Okay. So in type A, I'm going to first talk about two families of W algebras that naturally generalize the principal W algebras that I already mentioned. So let me take SLN plus M and think of it as being an extension of SLN plus GLM. So SLN is the upper block, GLM is the lower block. And then the rest of the W algebra has this decomposition of modules for SLN and GLM. So this means standard tensor, the dual of the standard for GLM. This is the other way. This is standard tensor. Sorry, the dual of the standard for SLN tensor, the standard of GLM. Okay, so this is how this algebra decomposes, and I take a nilpotent in SLN plus M, which is principal in the upper block, the SLN block, and trivial the other block. So every nilpotent corresponds to some Young diagram or some partition. And this is the we call this the hook type partition because it has one big block. This is the principal block, and then a bunch of trivial blocks. So this is shift level K plus N plus M. So this notation W, K, and M just means this W psi is the shift level. And this family is kind of a reasonably natural generalization of well-known examples. So N is 0. This is just the principal W algebra. So there's no trivial block. If N is 1, then there's just one trivial block, and this becomes the subregular W algebra. So N plus 1. I can also take M to be 1. This should say not. I can take N to be 1, and then this big principal block is another trivial block, and this just is the affine W affine vertical with SLN plus 1. And there's also the minimal local where I take the first block N to be 2. So this generalizes a bunch of well-known families. What is the structure of these W algebras? So, well, if N is 1, then the affine algebra is the Heisenberg algebra. So this H means Heisenberg algebra. If N is greater than 2, then the affine subalgebra is affine GLM, which is Heisenberg tensor affine SLM with some shift of level. And then because of the decomposition of the principal block with respect to this SL2, I have additional generators in weights 2, 3 up to n. And then I also have a bunch of even fields in weight n plus 1 over 2, which transform under GLN as the standard representation plus the dual. So there's exactly 2m of these fields. They have an action of GLN. This is the way they transform. Okay, so the case where n is 0, I have to define slightly differently. So in order to the result that I want to state holds uniformly for all n and m. So it's not that important here, but maybe I should just mention this for completeness. That when n is greater than or equal to 2 and n equals 0, these algebras don't come from philosophical reduction. These are just defined in a different way. So this is simply the tensor products of affine SLN at some level with the beta gamma system of random math. So the reason I define it this way is because there's similarly an embedding of this affine algebra GLN in this tensor product. So the Heisenberg part just lives over here, and the rest of it is a diagonal embedded. So I'm going to take the coset of the affine part, and the coset of the same affine algebra is mutable for this tensor product. And then 0, 1, and 0, 0 are defined degenerately. 0, 1 is just a beta gamma system. 0, 0 is just the complex numbers. Okay, so this is my family of even W algebras. It's relevant here. And then I'll define a similar family of super algebras of type A. So this will be, I take G to be SLN/M. And it has a very similar looking decomposition where there's an upper SLN and a lower GLN. The only difference is that this extra stuff is now fermionic. And I can again take a nilpotent, which is principal SLN and trivial and GLN. And there's a shifted level here, and this B psi NN is just this W super algebra. And the case where n is equal to n, I have to do in a slightly different way in order to get a simple W algebra. So instead of taking SLN/n, I have to take PSLN/n. And then I get something small. Okay, so again, this is a generalization of some known examples. So if n is 0, this is just the principal W algebra. Sorry, n is 0, it's just the principal W algebra. So it's not a super algebra. If n is 1, then it's principal W algebra, so n/1. If n is 1, this is trivial, and this is just an affine super algebra. And also, if n is 2, then this is a minimal W algebra. So again, this generalizes familiar families. So just like in the previous set of examples, the affine subalgebra is of type GLN if n is not equal to n. N equals 1, then this is just a Heisenberg algebra. If n equals n, then because I got rid of the Heisenberg algebra and I replaced SLN/n with PSLN/n, then the affine subalgebra no longer has an extra Heisenberg, it's just an SLN. Okay, so this also has some extra generators. So in addition to the affine algebra, there are some even generators of these weights that come from one principal block, and then there are the same looking fields that we had before, the 2m fields in weight n plus 1 over 2. They transform this way under this Lie algebra. The only difference is that those are no on fields because they come from the fermionic part. And again, I have to define some degenerate cases differently so that my result will be uniformly. When n is 0 and n is at least 2, then instead of taking a W algebra, I simply take this affine algebra tensor for the PC system. This is another field algebra, which is fermionic. And this also has a diagonal action of the appropriate affine algebra, so I can take this cosets. And then there's a few other degenerate cases. The 1-1 case is the rank 1, the symplectic fermionic algebra. The 0-1 case is just the PC system, and these two cases are trivial. So this is just designed so that it's stateful and uniform. Okay, so now I can consider the affine cosets of these algebras. Okay, so what does this mean? Well, this has an affine GLM. I take this affine coset. N is 1, this is just a Heisenberg coset. If n is 0, then there's nothing here. I won't do anything. That's just my W algebra. And similarly for the other cases. The NN case is slightly different because this algebra, this W algebra, has a U-volume outer homomorphisms. Somehow survives rid of the Heisenberg algebra, and I have to take the U algebra. This is the only case where there's a infinite group of outer homomorphisms. So I consider these affine cosets, and the main theorem here is that we have isomorphism between three of these. So this is a super algebra. This is isomorphic. So this is a coset of the super algebra. This means 1 over psi, and this psi prime is related in this way. Okay, so this was originally conjectured in different notation by Gaiotto and Rapcak in 2017. And the most important thing to say about this probably is that this generalizes simultaneously Feigin-Frenkel duality and the coset realization. So the first one, if I take m to be 0, this first isomorphism is exactly Feigin-Frenkel duality. So both of these are just principal W algebra, and this level shift is exactly the one we should get with Feigin-Frenkel duality. The other ones where I don't have n equals 0 anymore, but I have the same relationship between the levels, I want to think of as being natural generalizations of Feigin-Frenkel duality. So I call those isomorphisms of Feigin-Frenkel type. There's other one where I now have 2 Ds, and one of these components is 0, and this switches the role. This recovers the coset realization theorem in type A. So maybe it's not completely obvious that that's the case, because you remember the case 0n was an affine algebra tensor with a BC system. These BC systems are simply an extension of L1 FLN or L1 GLN. And if I take the coset of this affine thing tensor with the BC system, I get exactly the same thing as if I replaced it with L1 SLN. So this really is the coset realization theorem. And then there's another example that also has been studied. So this one is coset of a principal W algebra, SLN/1. This is the coset, Heisenberg coset of a subregular W algebra, SLN. And this is a case where the W algebra just becomes an affine super algebra, the coset of GLN SLN/1. The isomorphisms we use 3 was invented a long time ago by Feigin and Symétries, and this was proven differently by Thomas Creutzig. Should ignore it. So, anyway, so this is a general statement that subsumes some things that are known and also proves a number of other things. And I want to say a few words about the proof of it before I talk about generalizations. So the idea here is that it's not easy to prove that VOAs are isomorphic to each other, because most of these vertex algebras, most of the time we don't know the full structure of vertex algebras. You can't actually compute OPEs and write down a map. It's too complicated. Even for principal W algebras of type A, maybe up to SL7, you know the structure, but beyond that, we won't. So it can be done directly. Instead, we have to have some way of classifying vertex algebras of a certain type by some data that is easily computable. So this is what can be done in this setting. So the first thing is that I want to understand what the generating type of these cosets is. So when I think generating type, I mean strong generating type. So what is the minimal number of fields that close under OPE, maybe nonlinearly? And generating type typically means I write down a minimal strong generating type. At least I tell you which these fields appear. Okay, so it turned out that in all these cases, we can figure out what the generating type is. And they're all, so this notation W23 up to something, it's a physics notation, which means that it has minimal generating set consisting of a field in root 2, a field in root 3, a field in root 4, all the way up to this point, and nothing else. Okay, so how do you prove statements like this? So in general, it's hard, but for this class of VOAs, we can study the generating type using classical invariant theory. So the OPE algebra is complicated, but there is a large level limit of these W algebras, and actually all W algebras. It is simply a tensor product of two field algebras. And also there's a statement that says that if you pass the large level limit where things are simpler and you can write down a strong generating type with a limit, then that will give rise to a strong generating type for the downward generically. So it may not be minimal anymore. In these cases, it actually is minimal, which is not difficult to see. So anyway, so when we pass over a large bubble limit, then the W-algebras can be, the generating type can be studied using classical invariant theory. So these statements are actually, should be thought of as a formal consequence of Weil's first and second fundamental theorems of invariant theory for the GLN with its standard representation. So maybe it's a little bit of work to apply it, but that's essentially why these generating type. So the field of weights 2, 3 up to n, we already had from the principal block. The one that comes right after that comes from the pairing of these modules. We had these modules that transform under GLN as the standard dual standard. Weil's theorem tells you that if you pair a standard and a dual, you get a quadratic invariant. The first quadratic invariant is weight n plus 1 because the total weight of those generators is n plus 1 over 2. And then you keep going using the derivatives to generate this, and you get exactly this stuff. Okay, so now the question is, we have a lot of DOAs that have this generating type. How do we compare them? So again, I don't want to try to compare them directly, but I would like to classify them. And it turns out that there is a classification of DOAs of the generating type. They all arise as quotients of a universal object. So there's a big DOA, which is it's not defined over the complex numbers anymore. It's defined over the ring of polynomials in 2 variables. Which serves as a classifying object for these DOAs in the sense that any DOA that has generating type of this shape up to some point, satisfying some Weil hypotheses that are easy to track, is some quotient of this universal object. Okay, so this universal one is freely generated of this type, so it has a PW basis. It's a very large object. It's defined over this ring, and the weight 0 component of this large DOA is just a copy of the ring. So this is of C of T type in the sense of DOA that we rings. Weight 0 is just a copy of the ring. So you can get a lot of quotients by starting with ideals of the ring. So if I take an ideal, say a prime ideal of the polynomial ring, then I can let it generate a DOA ideal. Just take all the I-linear combinations that goes into DOA. That's a DOA ideal. And then I can take the quotients where I do 2 things. So the first thing I do is I just take the quotient of this ring, out of this ideal, and make some other ring R. And this quotient is now going to be the DOA over this ring R. So it turns out that the big DOA is simple in an appropriate sense. And one way to phrase this is it's simple for generic choices of the ideal. So if I just pick a random ideal, this would be simple. It will have the same generating type and rate of character as the big DOA. But there's certain discrete families of ideals where it's not simple. Essentially, it's because if you consider the Shapovalov form in the weight n space, and, if the Shapovalov form is degenerate, then you will have a singular vector of the again. And the Shapovalov form for DOA over the ring is just some element of the ring. And I can factor this. This is the factorization rate. If my ideal happens to be generated by one of the factors of these Shapovalov forms, then I will require a singular vector quotients. So this is the way that interesting quotients arise. And this is the case, I can give some other notation to the simple quotient. So this means that I've taken the simple gradient quotients of this DOA over the ring. And all DOAs of this type have this form, it turns out. So in particular, principal W-algebras of SLN all have this form. And then this ideal, the variety corresponds to what I call the truncation curve. This also are physics papers. So this is the invariant that I want. It turns out that one parameter of DOA is in bijection truncation curves. So I can tell when 2 of these algebras are explored simply by computing the truncation curve possible. So anyway, so these families that I introduced before, these cosets of the Hook-type W-algebras and superalgebras, they have this form. And it turns out that there is a mechanism for computing these truncation curves that is uniform for all n and m. And it's not that difficult. So the way one sets this up is that we already know that there is this W algebra that is an extension of an affine algebra tensor with some quotient. So if I don't specify yet what that quotient is, I know that this W algebra is an extension of this, and the extension is generated by fields in a particular weight, with a particular transformation behavior, and a particular parity. So that data, it turns out, uniquely characterizes this truncation curve in a way which is computable. So you can see it fairly early in the algebra. So you're able to calculate these curves, and they all have a nice form. Actually, there's more that's true. It turns out that the whole structure of this W algebra, all the OPs in this W algebra, are uniquely determined by this structure and this unique data, just the way that these extra fields transform in the GOF. So even though the OP algebra is complicated, it can be deduced recursively, completely just from this data. Okay, so you can find all the truncation curves for C, psi, and D psi, and simply from the explicit formula, we can see the trialities. It's simply a computation involving changes of parameters to these explicit forms of variables. Okay, so a couple of things maybe it's worth mentioning here. There's a bunch of consequences that you get from this. So one thing about these truncation curves, which is maybe surprising that physicists of course conjectured it, is that these truncation curves all intersect rationally with each other. So all pairwise intersections are nice rational points. And those pairwise intersections have a meaning. So you have two different one-parameter VOAs that have different curves. When they cross, which typically happens 3 times in this family, you get isomorphisms between the simple quotients of these algebras. And it happens always in those points. So there are certain well-known isomorphisms that get explained from this perspective. So one family is the so-called Paris-Bergian algebra of SL2. So you take affine SL2, you take the coset of the Heisenberg algebra, this one's the 10 elements. You get some VOA. That algebra is one of the ones in this family. And it's not, it's some algebra that's on this family. The generating type is W2345. But it turns out that when the level K is a positive integer, consider the simple quotient, those are isomorphic to positive integer K, is isomorphic to certain W algebra of SL K, a nice non-degenerate admissible level, which is rational. So this was proven by Tomiyuki and some other people a few years ago. And there are many more examples like this, where you have some algebra at some special point, which is isomorphic to W algebra. And that isomorphism can be reproven as corresponding to an intersection point in the curve for the principal W algebra and this parabolic algebra. Those are also not the only isomorphisms between parabolic algebras, principal W algebras. So you can classify them all by finding these intersections. Okay, so you have many pointwise intersections of ways. Sometimes you can deduce rationality of the way because it's isomorphic to some other real expression. There really get another way to see it. There are other things one can do with this result as well. Okay, so let me say a few general things about universal objects. So this W infinity algebra that I talked about is an example of universal objects. This was very important to prove this result. At least that's the only way at the moment that we know how to prove this. So a universal object should be, first of all, a vertical algebra that's defined. It has some prescribed generating type. So that case was W234X. It should be defined over a commutative range. In that case, that was just polynomials in 2 variables. And I want this to be a classifying object for VOAs of this type. I want it to be, in some sense, the biggest VOA that one can create. So how do you make this precise? I'm not quite sure what the best one is, but one thing that I definitely want is that it cannot be defined in a non-trivial way over a ring with bigger control dimension. So what that means is that if you have another VOA, say P prime, of the same generating type, and it's defined over some ring of higher Kroll dimension, then this extra stuff is essentially tensored along, comes along for the ride, and does not give rise to a moduli space that's higher dimensional. So in other words, B prime is just B tensor over R S, maybe after localized. So maybe S doesn't contain R, but after localization it does, and you can write it as well. So that's the case for the W. There's no meaningful way to define it over a larger ring. So there is a choice of coordinate. The way that I defined it and the way that I used it, I make a choice. So there are many different ways you can reparameterize. And I'm not sure if there's a canonical choice. One thing that I'm exploring with Thomas Creutzig is the possibility of compactifying the parameter space, defining this not over monomials and 2 variables, but the function on CP2. So this can be done, but it's not even fully clear. I'm not sure if there's That's what we do. But there's some meaningful sense in which this is the biggest viewer of its kind, maybe after I've chosen for this. And when you have such a universal object, there's at least two nice applications, things you can do with it. So one of them is that you can classify VOAs by strong generators. And you also can classify the non-trivial coincidences, the pointless coincidences among these VOAs by taking intersections of the truncation varieties. And these truncation varieties may not be curves anymore. There are many examples where this has many more parameters than just two. So the varieties will be subvarieties of the parameter space with some nice properties. So I expect that the intersections are always nice. Anyway, so this is what I mean by universal objects. And let me briefly mention that there is an analog of the triality theorem for ordered symplectic subs. I won't say very much about this because it takes a lot of implementation. But now, instead of having two families of VOAs, I have 8 families. So these Lie-algebras are now either BCD Lie-algebras, or there are some OSP superalgebra. And the decomposition is analogous to the type of type A. So there's two subalgebras A and B, and then everything else, which might be even or odd, will transform as a module over A plus B, and this is the standard A, and this is the standard B. So it's a little bit like we have before, except that there's no dual plus standard, because the dual is either all these standard representations are now self-dual. So the restrictions are that this B is either type B or type C. So that when I take a notebook in the principal block, I get generators of types 2, 4, 6, up to 6. And then A can be any of these 4 choices. And there's also a choice of, so this determines everything. For each choice here and each choice here, there's one Lie-algebra or superalgebra with this property. And I can consider the same. So these are what we call hook type W-algebras in Corpus symplectic types. I take the nilpotent, which is principal in this B block, and trivial in the A block, and I take these W-algebras. So now there's a bigger family. And the affine cosets, and again, affine cosets sometimes requires me to take an orbital. They are also portions of a universal object, and this is what we call the even spin W-infinity algebra. So it has generators of those 2, 4, 6, etc. This was constructed in paper with Shisheng Kanade a couple of years ago. And so there's a similar triality theorem that we're going to write down. It's a little bit complicated, but also instead of being just one family of trialities, there are 4 families. So these things break up further, and also depending on whether the parameters that were ranked are big, the rank of A or the rank of B is bigger than we belong in different families. So the story is more complicated, but it also is a statement which naturally generalizes the Feigin Frenkel dualities in types B, C, and D, also OSP 1, 2, and as well as the cosetization of those algebras, all those principal W-algebras. Okay, so the main thing that's new that I wanted to talk about today is how does this generalize, if at all? So the first thing that we need to try to address this is more families of more universal objects. And so we should look for families of VOAs that have the same generating type and look like they naturally belong in the universal object, and then try to construct these universal objects. So there are many such families, and I think the easiest ones to understand, you've never thought about this before, is type A. So I'm going to mostly stick to them. The thing I'm going to state is not type A. Okay, so let me start with rectangular W-algebras, which are a natural generalization of principal W-algebras. These were studied by Tomiyuki and Vladimir Kovalchuk a few years ago. And I'll also take some small variations on these. So let me take GL and M, equipped with the nilpotent F n to the M. So this just means that the corresponding tableau has n blocks of A n. Okay. So these are called rectangular W-algebras. And the generating type, there's a GLM in weight 1, and then there's M squared fields of all these higher weights that each transform this, the adjoint representation of GLM. Okay, there's some level shift for the affine subalgebra. And so you can think of this as a generalization of the principal W-algebra where M is 1, this is just the principal. Okay. So there is some uniformity to the generators, as you see. There's also a family which is So these are kind of like the principal W-algebras. In this family, I'm going to call these rectangular W-algebras with a tail. These are the rectangular analog of what we call quantiques W-algebras. So now I have GL_NM plus R, where in the NM block, I take this rectangular notebook, and then in this R block, I just take trivial notebooks. So the affine subalgebra, from the rectangular part, you have a GLN at some shifted level, and now you have a GLR as well. And so what I'm interested in here is I want to take not the full affine coset, but just the coset of this GLR part. So you can see that so first of all, what is the generating type of this? So you have, from the rectangular part, you have all the fields that I had before. And then I have a bunch of fields in the weight n+1/2 that would transform under GLR as a bunch of copies of the standard and a bunch of copies of the dual. And how many do I have? I have exactly R standards and R duals. So I can pair any of the standards with any of the duals and get some invariance. And so that's where I get these fields of weight n+1. I pair one of these copies of the standard into the dual, and I get exactly the square. And this pattern persists. So this is the part where the principal ones end, and the new part just continues to pattern. This can be worked out as important how high you go. So this algebra is no longer really generated, but it has this thing generating behavior. And there's also a similar statement for super algebras. Instead of taking GL_NM plus R for GL_N/R, I take the same notebook, principal rectangular in this block, and I get the same behavior. So it's natural to expect that for each fixed M, there's going to be a universal two-parameter VOA that has this generates. And this continues all the way. It's supposed to be pretty generated this time, such that all these examples are one-parameter quotients. And the case where n=1 is just the case that we already understand, except that because I started with GL rather than SL, I have an extra Heisenberg. Okay, so in fact, it's not so difficult to show that you have two-parameter algebras like this, but the universality is a difficult problem. So constructing this is a reasonable name for this algebra, somehow GLM analog of W infinity. So constructing this and proving that it's exactly a two-parameter algebra is quite difficult. It's not something that you can easily do without further assumptions, computationally. So, but there's a few things I can say about this. So one model for this is if I take n=1 in the story that I just talked about. So if I take n=1, then there's no principal blocks. So this is just an affine vertex algebra of GLM plus R. So this W algebra doesn't have. And this coset that I talked about, the GLR coset, is just the coset of GLR and it's bigger affine algebra. So this one, it's a little bit easier to get some intuition for. So of course it has the correct generating type. And you can write down generators for this algebra. So for each R, you have such an algebra. You can write down generators in such a way that the description of it is uniform for all R. And moreover, the OPE algebra, all the structure constants are rational functions of R. So having that information, it's possible to say that there does exist a two-parameter VOA, but this R is now analytically continues to the complex parameter. And so this is now a two-parameter algebra. So, and I think that should be, I'm sure it's expected that this is isomorphic to this universal one after some changing parameters, but you know, it's not easy to say that this is the universal one, but at least there's a model. And there's certain things that we know about this VOA in this model, which is that, so if I take the coset of GLN inside GLN+1, I have a W infinity quotient. This is one of the things on my list of W infinity quotients. And I can iterate this. So it's apparent from that description that this coset is an extension of the tensor product of M commuting copies of this W infinity algebra. And you can write down exactly which ones there are. It's also an extra Heisenberg algebra because it's started with GL rather than an SL. So this is the case for each one of those, and that should be the case for the universal object as well. So not only is this universal object, and we know it's generating scientifics, which has a lot of information. I think that if you try to construct it directly from that, it's too difficult. But if you impose the further condition that it be an extension of bunch of copies of the W-infinity algebra. Really, it's a much more attractive problem. It's still not solved, but I think it's a more usable way to think about this. This is an extra structure that we expect of not only this family, but all the other quotients. So I'm hoping that with that extra constraint, we can construct this. Okay, so let me say a few words about other types. Actually, I think I'm really short on time. So
you started 7 minutes
I
late.
just okay, so I try to be quick in here. So there are similar objects in other types. So there are the idea is that you have to look for the analogs of rectangular W-algebras and also the and so for SON, so this n can be even or odd. This algebra has slightly different weights in the type A case. So in weight 1, you have an affine SON, but then in weight 2, you have some fields that transform as not the standard, not the adjoint representation, but sin squared standard representation. So there's kind of alternating behavior. The even ones transform as sin squared CN, the odd ones transform as lambda squared CN, which is the adjoint. So this is currently under construction for Hans as a postdoc at my university. And so we expect also that these algebras should be tensor products of a bunch of even spin W-infinity algebra quotients. And the reason for that is that for each n, whether it's even or odd, this successive coset of SON, SON plus 1 is a W spin algebra. So you do this a bunch of times, and we expect that these algebras are like this as well as the universal object. And again, that may be something helpful in doing the construction. But in type C, the story is quite different because the coset of SP2n is the next SP2n plus 2 has a copy of affine SP2 in it. And this strong variant is like, again, using classical invariant theory, it's easy to work this out. There's three fields in weight 1 and just my SP2. And then in each even weight, there's only one field. In each odd weight, there's 3 fields. And the copies of 3 fields transforms the adjoint representation under the SP2. And so again, the usual story is that there does exist a 2-parameter algebra like this, where I simply replace n with a complex parameter, make some argument that the OPE algebra of these cosets is uniform in n. OPEs are uniform in n, which can be done. So you construct something, but it's by no means obvious that that's the universal. So, but my student, Vladimir Kovalchuk, who's graduating this year, one thing that he's did in his thesis, he's almost finished with this, is constructing this universal object and actually proving that it is the thing I just talked about. It's a 2-parameter object. So here I'm using C and lambda for my parameters, but actually one of the parameters can be taken to be K, the level of the affine density. Okay, so this construction is similar in spirit to my earlier construction with W-infinity algebra. It's a lot more involved. So the idea is that you, in addition to this affine SL2, you throw in a bunch of fields that are in even weights. These are SL2 trivial. So they're in even weights. So L is going to be the Soro, W4, W6, W8, etc. So I declare that I have these fields. And then in each odd weight, I have 3 fields that transforms the adjoints. Okay, so this is quite a strong constraint in the OPE algebra, just the existence of these fields, these weights, because everything has to respect SL2 symmetry. So there's a lot of restrictions on which SL2 modules can appear in the OPEs. But the problem is it's still difficult to do anything with. And then there's a further constraint, and there's something like this that I also imposed in my earlier constructions, where I assume that this W4 field is a kind of weighting operator. So it takes this field to this field. So things that I construct are highly non-primary, but there's a nice recursive behavior to the OPE algebra that use this as a weighting operator. And similarly, it takes these fields of weight 2i plus 1 to 2i plus 3. So this is a reasonable constraint. And in particular, this says that this VOA is finitely generated, but of course not strongly finitely generated. So, and then the idea, which is a very old idea in physics, that you write down the most general OPE algebra, which is consistent with all the symmetry, and you write down all the possible things that can appear with some undetermined constant, and you try to solve a big system. It's a big system of algebraic equations from structure constants. So, so that problem is in some sense deterministic, but it's difficult, and it's also infinitely many equations and infinitely many unknowns. So it's not obvious that this can be done. But what turns out to happen, first of all, is that this is a finite problem. So this was, I showed something like this in my earlier constructions, and Vladimir showed it in this case in a way which is quite general. So I think any problems like this, the finiteness can be proven from first principle without any computation. So the statement here is that if you know all the OPEs of these fields, where the weight of two fields has some less than or equal to 15, that determines everything else uniquely and constructively and compatible. So this, constructing this huge object is reduced to going up to the 15 and seeing exactly two undetermined constants that don't go away. And he's almost done with that finite computation. There's a little bit more computing to be done. But at least he's usually early in the computation with many undetermined constants. The deeper you go, you get rid of them. And we're at the point where we've had two for quite a while. There's a little bit more to prove that this is unique. It should work. So another thing I say that can be done with this algebra is get a theorem, because it's remaining the computation is completed. But there are quite a few things you can do with it. So one thing is, let me just, I think I have 4 minutes left.
Yeah.
Okay, let me see if I can quickly do this. So, so let me talk about a couple of natural examples of new ways to have this type. So I already mentioned these cosets of SP2 and SP2 plus 2. This is one example. So there's also 2 different objects that you might call rectangular of the appropriate type. So one of them is I begin with SO4n. And this has a subalgebra SP2n plus SP2. And this is how SO4n decomposes as a module for this. So this C is the trivial representation of SP2, and C3 is the angular representation of C2. So then I take the nilpotent, which is principal in SP2n. So from this description, you can see that well, you have to know how these 2 modules decompose under this SL2. But this one is the adjoint representation. So this one, because I take principal here, I get fields of which 2, 4, 6, etc. So those are those even fields, which I have 1 in each way. This group of them will give me the 3 odd fields in each way. So this has the appropriate type. And you can think of this as being like this rectangular W algebra, where the principal part is SP2n. I replace it with SP2n, and then the rectangular part I replace with SP2. So there's another rectangular object like this where instead of beginning with SO4n, I begin with a SP2 times 2n plus 1. And this has a slightly different decomposition. There's a type B rather than type C plus SP2. And now the rectangular part is still SP2, but the principal part is SO2n plus 1, which also gives the correct type. And now, which one of these is the adjoint gets switched, and this again has the same, the correct behavior. So these are a couple of families of rectangular behavior. And then more generally, I can look at rectangular with tail. So I simply look for algebras where the principal part is one of these 2 types. The rectangular part is still SP2, but this tail can be any of these 4. And for each one of these choices, in which there are 8, there's exactly one W algebra, W superalgebra. And so what I'm supposed to do here is take the tail coset, just like I did today. What remains, again, you have to check these at the variant theories. So the pattern of generating set persists, and you get a big family of cosets algebras, things that are of the correct generating set, and they should come from this universal object. Okay, so I think I'm very short on time, so let me just, I won't do all the slides, but I'll just say a few words. So all these families, so this algebra that Vladimir is almost done computing, we have enough data to find the truncation curve of all 8 of these families. There's a unique solution here. Can also show that the full OPE algebra of all these W algebras is uniquely determined by this data. You have this affine algebra, you have this quotient of this universal and an extension of a particular that really determines the OPE algebra. And so these truncation curves also are somewhat nice, and all the intersection points are rational. So once this computation is complete, you get many coincidences. So intersections of these curves give you nice coincidences. So the last thing, which I'm a little bit short on time on, is whether there are trialities, one parameter isomorphisms. So it turns out in these 8 families, there are not. you have 8 families with each indexed by 2 non-negative integers, and they seem all be distinct. But there are other ways that you can realize these algebras. So there's a family of W-algebras that's a little bit like this. They're also something like rectangular with tail. Instead of having SP2 as the rectangular part, you replace it with SP1, 2. So, and then you have a tail part, you say coset. You get something a little bit more complicated. But experimental evidence suggests that these larger algebras are tensor products of a hook type W algebra and one of the portions of this. So it's not obvious that these W algebras even have a subalgebra which is isomorphic to a hook type algebra. You can guess which one it should be. It should simply correspond to this tail and the principal block. But that seems to be the case. And it seems that if you take these larger W algebras and you take the coset of the hook type algebra, if you think to be there, we can prove it, you should get VOAs that are coming from this family with some shift of values. So these are conjectural statements. I'm also not sure how far it generalizes, but most likely they're true. Okay. Yeah, let's do this stuff here.
Thank you. We have time for some questions, please. Second.
Is there any reason why only classical particle types appear? Why not exceptional EFT?
That's a good. So in many statements, so even they do appear in Frenkel directions, but the co-serialization is only question. Because as far as I know, it's a question. I realize that. And so the ones that appear in these trialities typically belong in a family. So those are, it's quite possible that there's some way, and maybe there's some family. I have no idea.
So you've got this impressive web of isomorphisms between various types of algebras, vertex algebras. Can you say a little bit about how we can exploit these for the representation theory? Can some of these techniques also help us along there?
I guess that there's pointwise isomorphisms. So the pointwise isomorphism, sometimes you can prove rationality. So sometimes you have, so for example, you may have a W algebra of say type B or C, which is at a level that's not admissible, but it's isomorphic to a W algebra of some other weak type, which is not generally admissible. So that's known to be rational. So there's many examples like this. There's some that so pointwise isomorphisms, if you know something about one member of the common, you can say something. I mean, then there's one parameter isomorphism. So this is some work of Thomas and Trialities. There's a way of stooping up this isomorphism of affine cosets to a something that is a duality between the full W algebras. So one W algebra realizes some semi-topology of another intention with some kernel VOA. You have this map also is a functor and modules for one W algebra. It's not that. I should let Thomas explain this better. This is how it's. I think that's. I don't know. Is there anything else?
Yeah, so what Andy described is a generalization of Kazama-Suzuki, really vast one. But one more thing one can do is because some things are easier on one side than on another. And so, for example, if you have Lie theory, you can maybe have chances to classify. So usually the W algebra sides have chances that you do classification problems, and the super algebra side often has nicer finiteness properties. So this means you can prove certain things on one side, certain on the other side, and combine them to get really good results. Do we have any other questions? So then we will have a break. Let's thank Andy again once more.